Hi, everyone, and welcome back to Psych 3510. In this lecture, we are going to be discussing Chapter 10, which is titled Introduction to Simple Experiments. So, up to this point in the class, we've done a lot of heavy lifting. We've discussed a whole range of factors that go into research, the different types of research, different types of claims people can make. The sort of nuts and bolts like sampling and measurement and those sorts of things. We want to stop here for a second before this chapter and keep in mind that the term research is a larger, more umbrella term. And within that category, within the category of research, are experiments. Right? So, to be put another way, all experiments are research, but not all research can be called experiments. So, for example, correlational research, where we just measure ongoing behavior, right, and maybe do a correlation or a regression, that type of research is non-experimental because an experiment has a very special meaning in the world of science. And so this chapter is going to introduce us to the special meaning behind experimentation. So again, research is a broader umbrella term. Research is going to include frequency claims, correlation claims, and causal claims. But then a subcategory of research is true experiments, and only true experiments can make causal claims. So, we're going to go through a couple examples of experiments. We're going to discuss sort of the nuts and bolts, the bones of an experiment, different types of variables, how these experiments support causal claims, two large categories of types of experimental designs. Right? Not all experiments are the same. We can construct these experiments in different ways. And then we're going to briefly sort of map our four validities onto these causal claims. We've done this before at the beginning when we discussed causal claims, but here we're going to do it again with maybe a touch more detail after discussing how to build experiments themselves. So, an experiment allows us to make a causal claim, which is our most bold type of claim, that X causes a change in Y. They're not related to each other. One variable causes changes in another variable. So the advantage to a causal claim is that we can determine cause and effect, right? Maybe the ultimate goal of research, right? Understand exactly what causes something else to happen. As we've seen before, to determine causation, our experiment has to have three things. It has to have covariation, it has to have temporal precedence, and then we have to have basically internal validity. We have to rule out extraneous variables. We have to control for things. So what do we have to do to make something an experiment? Basically, we have to actively manipulate the world. We have to, as the experimenter, we have to go into the world and change something. This is mostly going to occur by putting people into groups, right? So group A, we do something to, and then group B, we do something else to, right? So maybe we're studying diet. So group A goes on a vegetarian diet. Group B stays on a normal diet, right? Maybe your typical American diet. And then we see some kind of health outcome, right? We end up with two groups of people. We have actively manipulated the world. We're forcing one group of people to stick with their normal diet. We're forcing another group of people to eat a vegetarian diet. And then we're going to follow up and maybe measure some health outcomes. So we have gone into the world. We've gathered participants. We have randomly split them into groups, and we have done something. We have changed something about the world, and then we're going to observe the effect of that change. Also, experiments can involve following people over time after we have changed something, and maybe introducing multiple changes to them over time. But we'll get to that later. So we're going to look at two sort of clean, easy examples of experiments. The first one is going to be on how different styles of taking notes impacts performance in class. And the second example is going to be how plate size impacts how much you eat. So in this first experiment, we have two groups of people. We have people who take notes on a laptop, and then we have people who take notes longhand. This basically just means writing notes on paper, right? You're using pen and paper. So we end up with two groups of people, the laptop people and the longhand people. They come to the same class, right? They're taking the same course, they're hearing the same information, and they're taking notes. Then we follow up with a test of their knowledge. And this experiment split knowledge into factual knowledge and conceptual knowledge. So what we have here is one independent variable. That's what we call the thing that we manipulate. So in this case, the independent variable is like note-taking or type of note-taking. And we have two options of that independent variable, laptop versus longhand. And then our dependent variable, our outcome measurement, right? The sort of the thing we're doing on the back end is knowledge, right? Maybe a score on a test. In this case, it's a score on essay questions. And these researchers just happen to also be interested in maybe the distinction between factual knowledge and conceptual knowledge. And so we can see, based on our bars, the laptop group in pink and the longhand group in blue, that in factual knowledge, we have very little difference, no difference between the groups. But in conceptual knowledge, the people who used written like pen and paper outperform the laptop people, suggesting something about writing down the information physically improves your conceptual understanding of the material. So we don't care so much about the finding here for our discussion. We care about breaking down what makes this an experiment. So what makes this an experiment is that we gathered participants and then we changed something about the world. We manipulated an independent variable, in this case, type of studying, or I'm sorry, type of note taking. We probably forced people into one of two groups, the laptop group or the longhand group. And then we followed up on the back end by measuring our dependent variable, our outcome, which here we could just call knowledge, right? Maybe score on an essay. So independent variable is the thing we manipulate. Dependent variables are the things we measure on the back end. So the independent variable causes a change in the dependent variable. That's what we're looking for. X causes a change in Y. And we can make that causal claim because we actively manipulated the world. We're not measuring naturally occurring behavior. We're not measuring things that are just happening in the world. We, the experimenters, went into the world and made a change. We manipulated the independent variable. A second example is you've probably heard about this. It got kind of a lot of press when this came out. Oh gosh, when was this published? I don't know, maybe early 2000s, mid 2000s, something like that. And what this experiment did was have people come into the lab, presumably doing something else, right? They were actually tricking them. They said, okay, we've got all these surveys to give you, whatever, right? Go do this stuff on the computer. Oh, thank you for coming in. We've provided an all-you-can-eat pasta lunch to say thank you for coming in to our experiment. As it turns out, the pasta lunch was actually the experiment of interest. All the other stuff they were doing was just distractors. So for half of the participants, they were given what was classified as a medium-sized bowl in order to dish their pasta into. The other half of the participants were given a large bowl to dish their pasta into. This was happening like one at a time, only one person in the lab at a time. So it wasn't like a big group thing. And so the question here is, does the size of the bowl cause a change in how much people eat. Or we have sort of a couple of variables here: how much pasta people serve themselves, like how much they actually take out of the serving platter and put into their bowl, and then how much they consumed, right? The experimenters were able to do this by, taking the plates, and they actually, in the back room, they're like measuring the amount of pasta and stuff like that afterwards. So they had ways of determining how much specifically was actually eaten. And so here we can see that the independent or manipulated variable is bowl size. We have two options, medium and large. And we're hypothesizing that that independent variable is going to cause a change in our outcome variables: how much pasta you either serve yourself or how much pasta you eat. Interesting tidbit, random piece of information. kcal is the actual scientific notation for calories. When you see calories on like a label on a food item, calories are actually kilocalories. So this is actually technically the correct scientific term for calories is kilocalories. Impress your friends the next time you see them with that. So the key to an experiment, again, is that we take at least one variable. In these examples, we're only going to worry about one. You can do more. That's for later. That's for like a different class. That's too complicated for us. We're going to stick with one variable that is manipulated, which basically means generally that we're putting people into groups, or, as we'll see later, we're doing multiple things to people over time. So we're manipulating something in the world, and then we're measuring the outcome of another variable. We're hypothesizing that the manipulated variable is going to cause a change in the measured outcome variable. The manipulated variable is called the IV, or the independent variable. The measured variable, the outcome, is called the DV, or the dependent variable. If this is helpful, a little trick to try and remember these is that the dependent variable is the one that depends upon the other variable, right? So the amount of pasta you eat depends upon the size of the bowl that you were given. Right? So the dependent variable is the one that depends, right? It's the outcome. It's the variable that we're proposing changes in response to manipulation of the first variable, the independent variable. Additionally, experiments will have good experiments should have control variables. These are things that the researcher holds constant on purpose in order to increase internal validity. So control variables are the things you want to control because you think they might have some like nefarious influence on your experiment. These are things that you want to exclude from the experiment, and we can exclude them from the experiment by holding them constant, right? So that they don't vary. Because if they don't vary, then they can't have an impact on our experiment. Excuse me. So for example, in the pasta study, we really want to make sure that we always give everyone the same type of pasta and the same sauce. It sounds like duh, of course, right? That you have to do that. But that's the point, is that it's a control variable that we need to hold constant because we don't want it to impact the outcome of the experiment. So if we gave people different pastas, if day 1 was marinara and day 2 was a pesto and day 3 was an Alfredo sauce, right? Then suddenly we have all this mess. We have all this fuzziness. We have all this uncontrolled change that's going on in the experiment. And so now I'm not sure if the amount of pasta people eat is due to the plate size or if it's due to variations in the pasta, right? Maybe the pesto is amazing. It's like the best pesto that anyone's ever had. And so, of course, people eat more of the pesto than they do the marinara. That's going to impact the experiment in a way that I don't want. I'm not interested in variations and types of pasta. I'm interested in bowl size. So what I want is bowl size to be the only thing that varies between my groups, and I want to hold everything else as constant as possible. So in this pasta bowl experiment, I definitely want to hold the type of pasta and sauce constant. I probably definitely want to hold the time of day constant, right? I need to be serving everyone at noon or at 1, right? Who wants, a big bowl of pesto at 7:45 in the morning, right? Probably going to impact how much people eat, especially if some people are getting the pasta at 7:45, some people are getting it at 10 a.m., some people are getting it at 3 p.m. It's just a mess, right? There's this mess now in the experiment. I want to hold it constant and control that variable of time of day. Things like that. You want to control the size of the serving platter, right? We want the place where they dish the food out from to be the same every time, the same platter with the same sort of standardized amount of pasta, because the size of the platter might dictate how much pasta people take. And I'm not interested in the size of the serving platter. I'm interested in how the effect of the size of their bowl. So you can sit here and think up, off the top of your head, 5, 10 control variables very easily that we're going to want the experimenter to control. This is also something is a good place to look at critiques of an experiment when you are reading an experimental paper and you're trying to decide how valid its conclusions are. You want to critique it based upon the goodness of its control variables, right? How effectively it controls these potential extraneous variables. Really strong experiments will control variables of importance that need to be controlled. If they don't control them, then the experiment might lack internal validity, because you might have this other third variable creeping in that's going to mess up the causal effect of independent to dependent variable. Again, we need covariance, temporal precedence, and internal validity to support a causal claim. So our experiments give us this third one, right? Internal validity. Covariance and temporal precedence can be achieved in correlational studies, right? Those can easily be achieved in correlational studies. What true manipulation and control in a real experiment, what those give us is the establishment of internal validity. So there's lots of terminology here that will vary, which is a little frustrating with experiments. So you'll hear things like comparison group or comparison condition in an experiment. Those things have to do with the independent variable. So let's go back to our diet study with people who stay on their normal diet and then people who do a vegetarian diet. So the vegetarian diet is like our group of interest, right? We want to see what the effect of going vegetarian has on people. We're going to compare them to the people who've done nothing, right? That is going to be called a control group, right? The people who are essentially controlled to be the point of comparison to the other group. Basically, a control group doesn't get a treatment. Right? Nothing is done to them. They are held constant or normal. And then they're the benchmark, the source of comparison for the group that actually got, the independent variable. You'll hear these different groups often called different treatment groups or treatment conditions. And then you have experiments that occasionally have placebo groups. The easiest example of this is, medical research, where We're testing the effect of a new medication, and one group takes a sugar pill. They don't know it's a sugar pill. They're naive as to whether they're taking the medicine or taking a sugar pill, but they're going to be our placebo control group. So a lot of this terminology is flexible. Just know that essentially when it comes to the independent variable, you're generally going to be putting people into groups, and then you're going to be comparing those groups against each other. We can call those things different conditions. We can call them different treatments. We can call them comparison groups. Groups that have nothing done to them are often called the control group. Groups that get a placebo, that get sort of like tricked a little bit, they're called the placebo group or the placebo control group. Lots of terminology here. What's more important than memorizing all the terminology is just understanding the concepts, like what's going on here, which is we're splitting people into group, we're manipulating something across those groups, and then we are measuring the impact of that manipulation on the back end. Quickly, though, please don't confuse control group with control variable. A control group is a defined group of people who basically do not get the independent variable. They're the people who we ask to change nothing, right? Or they're the placebo group, right? They're not getting a treatment. They're not getting anything new. The other groups are getting new stuff. They're getting the new diet. They're getting the pill. The control group is a group that we hold constant, but that's different from a control variable. A control variable is a variable we hold constant across all groups, like time of day or type of pasta in the other example. So let's make that a little more clear with, let's stick with a medical example. So we have, maybe we have two groups of people. Group one gets a sugar pill. They're the placebo control group. They think they're taking a medication, but they're actually not. And then the second group is actually taking, let's say, a blood pressure medication. We're hoping to lower these people's blood pressure. So group one, sugar pill, control placebo group. Group two is a treatment group. Right? They get the medicine. So our group that's taking the sugar pill is a control group, but a control variable that I might want to control across the experiment is age of the participants, right? If we're studying blood pressure, we know that age impacts blood pressure substantially. So what I might want to do is make sure that everyone in my groups, everyone in the experiment is between 65 and 70, let's just say. We control age for everyone. That's a control variable because it goes across the entire experiment. A control group is just my group that gets the sugar pill, or just my group that does nothing. They don't change anything about their lives. They're the sort of the benchmark, right? They're the comparison point. Okay. When we're talking about these control variables, we need to discuss some examples of why they're important, right? Some things that could happen, some types of things that can happen if we don't have good control. And what can happen if you don't have good control is a confound. So confounds, you can think of confound as also meaning to confuse. They are alternative explanations that threaten our internal validity. These are those nefarious variables, right, making their way into the experiment, and we wish they weren't. We wish that they were having no effect because they're undermining the integrity of our experiment. So in the pasta example, if we had pesto, marinara, Alfredo, if we were just mixing up the pastas, then type of pasta is a confound. It is a potential alternative explanation for our results that we don't want. It's not what we're studying. it is going to confuse our experiment and threaten its validity. So, confounds is sort of the general term. And then within confounds, we can have different things like selection effects and order effects. We'll get to those, yes, in just a slide or two. So another word about confounds. Design confounds are problematic when they imbibe systematic variability into our experiment. So if the pesto systematically, that means every time, consistently, the pesto is consistently tastier than all the other pastas, then we have systematic variability in a design confound, because the people that get the pesto are going to systematically behave differently than everyone else. They're going to predictably behave differently, but it's not a change that we want. It's bad variability. It's variability that we want removed. So that variability is most problematic when it's systematic, when it's consistent. There is unsystematic variability that can affect any experiment randomly or haphazardly. These are not considered confounds, but they are problematic. So unsystematic variability is things like, randomly one of your participants gets in a car accident the morning of the experiment, and getting in the car accident just throws them off, right? They're not behaving normally. They're sort of a different person than they typically are on any given day. And you can't control that, right? It's just this one-off individual that's randomly going to behave differently today than they would have behaved any other day. Or in our pasta experiment, you just happen to have one individual who stayed out super late last night and ate a whole bunch of Taco Bell at 3 a.m. So they ate a whole bunch of Taco Bell at 3 a.m. They roll in hungover, feeling bad, and full, and they're just not interested in eating pasta at your experiment. So that has nothing to do with your experiment. It is random variability that you cannot control, right? You can't, it's very difficult to stop someone from doing that. So it's unsystematic. It's just kind of coming in from all over the place. It's problematic, but it's not as problematic as systematic variability. We will always have random variability or unsystematic variability because humans are messy. Psychology studies human behavior. Human behavior is messy. So it's always going to happen. You try to keep it to a minimum. There are some things you can do to try and help with unsystematic variability. You're doing some like pre-screening of your participants, giving them some like behavioral guidelines, maybe leading up to the experiment, things like that. But this is basically the shit happens of experimentation. Sometimes shit just happens, and it sucks. And sometimes you don't even know that the shit happened, right? The person who got in the car accident might not divulge that information to you. You are completely unaware and naive that they got in a car accident, that they're flustered, that they're not behaving normally. You never know. They leave your experiment and you have their data, and it goes into the data file. So systematic variability is more problematic. It's also easier to solve because we can control for it. We can do things like hold the pasta constant. Unsystematic variability is less problematic because, like, on the whole, random variations sort of even out-ish, right? If you have enough people, if everything else is designed well, if you have a large sample size and you've done everything that you should do, the random variability should kind of even out around the edges, and it shouldn't be too much of a problem. So generally, it's less problematic. But the issue with unsystematic variability is that we can't control it. I can't make people not messy. I can't make shit not happen, right? Shit happens. So keep that in mind when thinking about confounds. Confounds are systematic issues with your experiment. They are not random alterations in human behavior. So, one type of confound is a selection effect. A selection effect is when you have a systematic problem in the way that you selected your experimental subjects. So, if I'm doing my blood pressure medication study, and I gather participants from a local gym, right? Let's say I go stand out. I right down the street from my house. There's a really busy gym. I go stand out there. Anyone who looks like they're over 65, I approach them. I ask them if they are over 65, they'd like to be an experiment on blood pressure medication, whatever. So that's problematic because I'm selecting participants that are probably not representative of the population. I'm selecting participants who are going to work out in a gym. Those people probably systematically vary in their health, in their workout behaviors, and thus probably their blood pressure from the general population, right? From the sort of average of everyone else. So I'm no longer doing an experiment on the blood pressure medication. I'm doing an experiment on how the blood pressure medication impacts people who work out. That's not what I want, right? It's a selection effect. I have a systematic confound from the way I selected my participants. You can also have selection effects based on how you split people maybe into your groups. And so we can use random assignment, right? Think back to the chapter on sampling. All of those strategies we can use that involve randomness can help us avoid these selection effects. But the key here is that if you select your participants inappropriately, you have a design confound. One really interesting thing you can do is engage in a matched groups design. So if I'm going to have two groups, let's say let's go back to the blood pressure experiment. People 65 to let's say 70, half of them are going to take the placebo pill, half of them are going to take the blood pressure pill. One thing I could do is collect data from or collect people, right? Get participants, and then I randomly assign them into either the placebo or the medication group, and that's fine. There's nothing wrong with that. If I want to be super careful about controlling for stuff, and this is often what medical studies do, then I match pair or I match group my participants, where I say, okay, I'm going to put this 63-year-old white male in the placebo group. So I need to match that person with a 63-year-old white male in the medication group. And then I have a 70-year-old Latin female. I need to match that person with another 70-year-old Latin female in each group. So that when you look at your groups, you're matching them on other essentially control variables of interest. Oftentimes, this is gender, race, age, ethnicity, things like that, that we know impact people's behavior, people's health. And so when we're doing our multiple groups, we want to make sure that we're keeping those groups even and controlled across those variables. We are going to, I realized I forgot to mention order effects. We're actually going to come back to order effects later in the lecture. So just sort of put a pin in that, and we'll mention again that those order effects are a type of design confound, but we're going to get to those in a few slides. Okay. So this is going to be a good stopping point before we move on to the next part. But I just want to introduce the idea that when we're designing these experiments, when we are manipulating an independent variable, controlling control variables, and then measuring a dependent variable, we do this in two major categories of designs. We have an independent groups design. You'll often see this called a between groups or between subjects design, and a within groups design, also called a within subjects, repeated measures, or dependent groups design. Again, lots of terminology here. I'm sorry, I didn't make this up. Don't kill the messenger. You will hear within each of these categories, you will hear these terms used interchangeably. So just try to know them all. And in fact, I will probably be guilty of using them interchangeably. They all mean the same thing. So an independent groups design is one in which I split my participants, like we've mostly been talking about. I split them into multiple independent groups, and those groups are separate and different from each other. So the people in the medication group is a whole different group of people. It's a separate group of people from the people in the placebo group. It's 50 people and then 50 other people. In a within groups design, what ends up happening is that I measure the same people over and over and over again. So I repeatedly measure the same individuals, and I give them each the different levels of my independent variable. So this can either occur over time, right? So maybe I'm measuring something from change in something in adolescence from 15 to 18, and I follow the same people over time, right? Measuring them repeatedly over time. That's a within groups design. Also, a good example of a within groups design is like a focus group. So let's imagine that you go in for a focus group on, I don't know, from Little Debbie, right? The little cake snack company. And they're doing a focus group on this new cake that they've developed. And they want the group to taste 3 different flavors, right? Vanilla, chocolate, and lemon. And so each individual tastes the vanilla, each individual tastes the chocolate, each individual tastes the lemon, and they provide their opinions and ratings. I have repeatedly measured the same group of people across my independent variable, which is flavor of cake in that example. So in an independent groups design, we have completely separate groups of people, and each group only gets what we call one level of the independent variable. They get one essentially manipulation of the independent variable. In a within groups design, I take the same group of people and I measure them multiple times repeatedly, and they get different level. They get multiple levels of the independent variable. They get the vanilla and the chocolate and the lemon cake. One group of people going across all levels of the variable, rather than having 3 groups of people, right? A vanilla group, a chocolate group, a lemon group. So when we come back for part 2, we're going to be discussing the details of these different types of designs, the advantages and disadvantages of each. So thanks, everybody, and I will see you for part 2.